Alright everybody, what's going on? This video we're going to look at mathematical induction. We're going to look at several examples, proven stuff using mathematical induction. So let's go ahead and get started. So here we have the principle of mathematical induction. It says let P of n be a statement involving the positive integers n. And if P of 1 is true, so if P of 1 is true, so if it's true for n equals 1, and for every positive integer k, the truth of P of k implies the truth of P of k plus 1, then the statement P of n must be true for all positive integers n. Alright, so first thing we need to show that it's true for P of 1. And then we're going to assume it's true for P of k, and then we have to show that it's true for P of k plus 1. All right, and you know that may not make sense to you right now, but let's get working into the examples and see if that kind of clears it up. So the first thing that we're going to do before we start proving things. So right now we're not proving anything. I've got a couple of problems here, 4 of them, where all we're doing is we're finding the statement P of k plus 1. All right, that's all we're doing right now is finding P of k plus 1. All right, so to do this, what they're wanting us to do is just take the k plus 1 and plug it in. So I've got S of k plus 1 is equal to k plus 1 squared times k plus 1 squared over 4. So all I did for each one of the k's, I replaced it with k plus 1. And so this is equal to k plus 1 squared times k plus 2 squared over 4. And this is all they're wanting you to do. Okay, so just keep in mind we're not proving anything right now. We're just practicing finding P of k plus 1. All right, so let's look at number 2. So we have S of k plus 1 is equal to 1 plus 5 plus 9 plus ... plus, and now let's put in the k plus 1. So that's going to be 4 times, and that's going to be k plus 1. So I'm just plugging the k plus 1 in, minus 1, minus 3. Okay, so I'll put the k plus 1 in for this k, which is right here. And then plus, and then I've got 4 times k plus 1 minus 3. And so now we're gonna simplify this stuff inside the parentheses. And so I get 1 plus 5 plus 9 plus ... plus, and then this is going to be 4k minus 3. So all I did is I just distributed the 4. Okay, I distribute the 4. Well, I guess not really distribute the 4. I mean, I did, but look at this. See, this 4 here. This 4 here is times everything inside the brackets here. So if we do k plus 1 minus 1, the 1's cancel out, and I'm left with k. So 4 times k is 4k, and then minus the 3. And then plus, and then this is going to be 4k plus 1. See, so this right here, this is 4k plus 4, and then minus 3, and 4 minus 3 gives us the 1. And so this is what they're wanting. All right, so now this one, so we're just going to replace each k with k plus 1. So this is going to be k plus 1 plus 3 is less than 5 times k plus 1 squared. And so this is going to leave me with k plus 4 is less than 5 times k squared plus 2k plus 1. And then, just leave it like this. No reason to distribute the 5. Now, how did I get this part right here, this k squared plus 2k plus 1? Well, that's folding this out. Remember, that's k plus 1 times k plus 1, and I just fold it out. All right, and then so this last one here, this would be what? 3 to the k plus 1 is greater than or equal to 2 times k plus 1 plus 1. And so this is going to be 3 to the k plus 1 is greater than or equal to, and then this is 2k plus 2 plus 1, distribute the 2, and then 3 to the k plus 1 is greater than or equal to 2k plus 3. And there you have it. All right, so that's all that was just, okay, let's plug in k plus 1. Let's practice that before we start proving these things. Now, let's start proving them. Okay, so it says use mathematical induction to prove the following formula. So we have S of n is equal to 1 plus 3 plus 5 plus 7 all the way to 2n plus 1. So this is summing the odd integers. All right. All right, so remember what it says. We have to show that it's true for p of 1. Well, or in this case, s of 1. So here for n equal 1, I have s of 1 is equal to, well, that's equal to 1. This 1 right here. All right. All right, so, well, and actually I didn't write the whole problem, n squared. In other words, we have to show that this is equal to n squared. So s of 1 is equal to 1, this 1 right here, and then that is that equal to when I plug the 1 into this? Well, that's 1 squared, and we know 1 squared is 1, so 1 equals 1, so it's true. And then we assume that s of k equals 1 plus 3 plus 5 plus 7 plus and I'm sorry about that. I actually wrote this problem wrong. That should be a minus there. Well, what a video this is starting out to be, huh? But anyway, yeah, it should be 2n minus 1, not 2n plus 1. All right, so I assume this is true. And so now I must show that s of k plus 1 is equal to k plus 1 squared. All right, so this is what we have to show. So we showed that it's true when n is 1. Then I assume that it's true for s of k. And now I have to show that s of k plus 1 is equal to k plus 1 squared. That's what the induction principle says. All right. So let's do that. So I've got s of k plus 1 is equal to, now I'm going to plug the k plus 1 into this, and then I'm going to see if I can end up with k plus 1 squared. So this is going to be 1 plus 3 plus 5 plus 7 plus all the way to 2k minus 1 plus, okay, so now what I'm doing is I've got to go to the next term. See, this right here, when I plug the k in, this is just going to k, and then I'm going to add on, it's like I'm going to add on the next term, which would be, what's the term after k? It would be k plus 1. And so that would be 2 times k plus 1 minus 1. Okay, I'm going to the k plus 1 term. See, the s of k term goes to here, which stops right here. And then I've got to go one more term because I'm going k plus 1. So there's that term. All right. And so I get 1 plus 3 plus 5 plus 7 plus, and that's going to be 2k minus 1 plus, and that's going to be 2k plus 2 minus 1. All right, so I just distributed, all I did was distribute the 2 here. And so this is going to be 1 plus 3 plus 5 plus 7 plus 2k minus 1 plus, and then that's going to be 2k plus 1. All right. So now, what do we do? Well, if you look at this right here, you see that right there? What is that? Well, this part that I have marked off in red, that's s of k, right? You see that? See, this in red is the same thing as this. That's s of k. And so that's s of k plus 2k plus 1, which equals, now what's s of k? Well, remember, we assumed s of k is equal to k squared. We assume that's true. So I'm going to replace s of k with k squared. And then that factors into k plus 1 squared. And so I've shown that s of k plus 1 is equal to k plus 1 squared. And so that proves it. All right, so let's look at the next example. It says prove that n is less than 2 to the n for all positive integers n. All right, so first thing, for n equal 1, 1 is less than 2 to the first, which that's true, 1 is less than 2. So I've shown that it's true for n equals 1. Now we're going to assume that k is less than 2 to the k is true. So we're going to assume this is true. And now we must show that k plus 1 is less than 2 to the k plus 1 for n equal k. So what does that do? Well, how do we go about proving this? Well, we've got 2 to the k plus 1 is equal to what? That's equal to 2 times 2 to the k. Okay? All right, so all I did, remember, when you have like bases and you multiply, you add the exponent. So 2 to the 1 times 2 to the k, well, that's 2 to the k plus 1. I just broke this up into 2 times 2 to the k. Now we need to come up with an inequality. So we know that this is greater than 2 times k, which is 2k. All right. So how do we know that? Well, this is by the assumption, because look, you see what I have up here? K is less than 2 to the k. And what do I have? Well, let's look at it piece by piece. K is less than 2 to the k. See, we assume that up here. And if k is less than 2 to the k, well, I can multiply by 2, and that's still going to hold true. You see that? All right, so now what do we do? Well, because two k is equal to k plus k, right? I'm just breaking this up because k plus k is 2k. And that is greater than what? K plus 1 for all k greater than 1. See, we've already shown that this inequality up here is true for 1. So everything larger than 1, I know this right here is true. Okay, just think about it. 2 plus 2 is 4, 2 plus 1. Okay, because see, to this k I'm only adding 1, but here I'm adding the k twice. All right, so what does this give us? This gives us 2 to the k plus 1 is greater than 2k. See, I showed that here. See, 2 to the k plus 1 is greater than 2k. All right, which that is greater than what? 2k is greater than k plus 1. Or we can write what? K plus 1 is, see the inequality symbol, less than 2 to the k plus 1. And that's what, and you see there, that's what we had to show. And we showed that there. All right. All right, let's take a look at the next one. Prove that 3 is a factor of 4 to the n minus 1 for all positive integers n. All right, so we've got, for n equals 1, we've got 4 to the 1 minus 1 equals 3. So that shows 3 is a factor. Okay, that's divisible by 3. Now we're going to assume 3 is a factor of 4 to the k minus, 4 to the k minus 1. I wrote the 1 in the exponent and it wasn't supposed to be there. And so now we must what? We must show, and keep in mind we're assuming this is true. Now we must show 3 is a factor of 4 to the k plus 1 minus 1. So how do we do that? Well, we have 4 to the k plus 1 minus 1 is equal to, now what we're going to have to do here is we're going to have to add 0 to this term, to this statement right here. We're going to have to add 0. But how do we add 0? Well, that's the same thing as 4 to the k plus 1 minus 4 to the k plus 4 to the k minus 1. So you can see here I'm adding 0 because negative 4 to the k plus 4 to the k, that's 0. All right? So I'm not changing this up any, I'm just adding 0 to it. All right. Now, let's write this as 4 to the k times 4 minus 4 to the k. And I'm going to group these terms together. And then plus, and I'm going to group these last terms together. All right. And now with this one, I'm going to factor out a 4k. So 4 to the, factor out a 4 raised to the k. So that's going to leave me with this, 4 to the k times 4 minus 1, if I factor out a 4 to the k, plus 4k minus 1. And so this is equal to 4 to the k times 3 plus 4 to the k minus 1. All right. So there we have. We have it. Look at this. Because because 3 is a factor of 4 to the k times 3 and 4 to the k minus 1. See, 3 is a factor of both of those. It's a factor of this first one. See, whatever this is, we're multiplying times 3. So we know 3 is going to divide into that. And this 4 to the k minus 1, well, that 3 is a factor of that. That's what we assumed up here. We assumed that to be true. So since it's a factor of both of those, 3 is a factor of 4 to the k plus 1 minus 1. And where'd that come from? Well, look at it right here. You see this? I said 3 is a factor of each of those terms. So that means it's a factor of all of this. And what does all of that equal? Well, it equals this, 4 to the k plus 1 minus 1. So if 3 is a factor of this, then it has to be a factor of this because they're equal. All right. So let's look at the next problem. All right, so our last example here. We want to prove that the sum I equals 1 to n of I squared is equal to n over 6 times n plus 1 times 2n plus 1. All right, so we've got to show that it's true for n equals 1. So for n equals 1, we have summation I equals 1 to 1 of I squared. So we're going to plug the 1 in. That's 1 squared, which is 1. So that's the left-hand side. We plug the 1 in for n, and we showed that equals 1. Now we need to plug the 1 in over here for n on the right-hand side and show that equals 1. So 1 over 6 times 1 plus 1 times 2 times 1 plus 1 is 1 over 6 times 2 times 3, which that's 6 times 1/6 is 1. So it's true for n equals 1. And now we're going to assume that it's true for k. Okay, so all I did, I just replaced the n's with the k. All right, and now we must show that the sum I equals 1 to k plus 1 of I squared is equal to, now I'm just going to replace each of these n's with a k plus 1. And so that's going to be k plus 1 over 6 times k plus 1 plus 1 times 2 times k plus 1 plus 1. Okay, I've got to show that those are true. Now I got to show that this is true. All right, so let's get started showing that. So I'm going to rewrite this left-hand side as the summation I equals 1 to k I squared plus k plus 1 squared. All right, now how in the world did I get that? Well, let me show you. Okay, so you don't, if you're taking notes, you don't have to write this part of the problem down. Okay, you don't have to write this down. I'm just showing you how I went from this to this. So if you look at this left-hand side up here, okay, look at this left-hand side. If I start listing these terms out, that's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared, and so on. And then all the way up to k plus 1 squared. So I could write in the k squared and then the k plus 1 squared. All right, so that's just writing all these terms out. All right, all the way up to k plus 1. Now, look at this. You see this part right here, just this part. Well, that we assume, well, we didn't write it out, but this right here, if we write that as a summation, that's just, instead of going from I equals 1 to k plus 1 of I squared, see, which is this entire thing, we're just going to k. So this k plus 1 would become a k. You see that? And this is this part right here, and then plus, see, plus k plus 1 squared. So that's where that came from. All right, and that is equal to k plus 1 over 6 times k plus 2 times 2k plus 3. All right, so where did that come from? Well, the 1 plus 1 gives me the 2, and then 2k plus 2, and then 2 plus 1 is 3. All right. All right. Now, what do we have? Well, now we have k over 6 times k plus 1 times 2k plus 1 plus k plus 1 squared. All right, where did that come from? That equals, and then that equals this over here. Where did this part right here come from on the left-hand side? Well, you see this summation right here? That's this part. You see that? Because this is equal to this. Where did that come from? Well, we assumed that was true. So I just replaced this with this. And now what I need to do is I need to multiply. I'm going to full this out. I'm going to multiply this out, and I'm going to multiply these two together. Okay? So that's going to give me k over 6 times, and that's going to be 2k squared plus 3k plus 1 plus, and then that's going to be k squared plus 2k plus 1. All right, so for this, I fold these out. And then for this, well, remember, this k plus 1 squared is k plus 1 times k plus 1. And then I just fold that out. And then that equals k plus 1 over 6 times, and now I'm going to multiply this out. That's 2k squared plus 7k plus 6. And now I'm going to distribute the k. And so that's going to be 2k cubed plus 3k squared plus k, and that's all over 6, plus k squared plus 2k plus 1 equals. Now, what I'm going to do is I'm going to multiply this k plus 1 times this. And remember, to do that, you multiply the k to each term and then the 1 to each term. And so that is going to give me 2k cubed plus 7k squared plus 6k plus 2k squared plus 7k plus 6, and all that over 6. And now what do I do? Well, now for the left-hand side, I'm going to get a common denominator, which is 6. And so that's 2k cubed plus 3k squared plus k. And then for this one, I have a denominator of 1. My common denominator is 6. So I've got to multiply this numerator by 6. So that's 6k squared plus 12k plus 6. And that equals, and then I'm going to combine like terms in the numerator here. And so that's 2k cubed plus 9k squared plus 13k plus 6, and that's all over 6. And now we'll combine these two fractions. So all I have to do is multiply the numerators together. So that's 2k cubed plus 9k squared plus 13k plus 6, that's all over 6, equals 2k cubed plus 9k squared plus 13k plus 6, all over 6. All right, so look at this. I've shown that those two sides equal the same thing, so that proves it. All right, so I know this proofs by mathematical induction, they can get kind of complicated. They can get kind of tough. But now you have several examples worked, and you have methods of proving these things now. So I hope this video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see y'all later.